Hi everyone, welcome back. In this section we're going to introduce equations of lines and planes in 3 dimensions. Now the reason these things are going to be important for us is because in calculus what we are interested in doing is taking curvy objects and approximating them with straight or flat objects. And so the straight or flat objects we will be using are going to be lines and planes. You can think back to Calculus 1 where a lot of times the question boiled down to a question about what is the tangent line to a curve. Well, in this course, in 3 dimensions, we'll be interested in tangent lines to curves, but also tangent planes to surfaces. So lines and planes form our fundamental objects. And it's in this section where we introduce lines and planes and how to represent them with equations. So let's just go with a quick reminder. A straight line is determined by 2 points that lie on it. Or another way to say this is if I have 2 points, then that defines a unique line that passes through them. So here's our problem. Our problem is, given 2 points in space, let's determine the line that passes through them. Now we can do this in a few different ways. So here I've got 3 equations for a line, and it depends on how we want to represent the line. So the first one involves vectors. So let's start with a coordinate system, our 3D coordinate system. And suppose we have a line in space, maybe something that looks like this. Now the idea is we're going to be given 2 points on this line, and we can just figure out how we can work with that. We may not be directly given 2 points, but the idea is that if we're asked to find the equation of a line, we're going to have some way of finding 2 points that lie on it. In this particular case, we are given a point on the line that's given by its position vector r0. So we've got some point on the line, and there it's given by a position vector r0. And we also have a vector that is parallel to the line. So I'll just draw that over here. We've got this vector v that's parallel to the line. What can we do with this? Well, the idea is I want to, using these 2 bits of information, figure out what are all the points on this line. I want to describe all the points that live on this line. So here's an arbitrary point. How could I describe it? Well, to describe that point, I'm actually going to describe its position vector. We'll call that r. So how could I describe that position vector to that point? Well, the idea is I can go along r0 to get on the line. Once I'm on the line, then I know the line goes in the direction of v, so I just need to figure out what multiple of v gets me out to the point I'm interested in. So that multiple, I will use t to denote that. So to get out to that point given at the tip of r, the way I would do it is I would first go along r0, which gets me to a known point on the line, and then go along the direction vector of the line, however far I need in order to get to the point. And so that's our parameter t here. If I take t to be positive, it's sort of shown here in this diagram. I'm kind of drawing it where t is positive. Maybe I'll just indicate that here. This is a picture when t is positive, just because of the way I've drawn v in the bottom left-hand corner. But suppose I wanted to get to a point here. Well, I would do the same thing. I'd go out along r0 to get a point on the curve. And then what I'd do is I'd just travel along the curve, or the line in this case, in this direction, some multiple of v. In this case, v or s would be negative. That multiple of v I'm using would be negative because I'm going opposite the direction of v. So the idea is I can get to any point on this line by first going out to one point on the line and then traveling along the direction vector, some multiple of that direction vector, to get to the point I'm interested in. So this is a way of describing all points on the line for various values of our parameter t. This is known as the vector equation for the line, and that's what we have right here. Now from that vector equation, we could unpack it. We could say, well, R is just some position vector of an arbitrary point x, y, z that's going to live on the line. R naught is a position vector for a point that lives on the line, x naught, y naught, z naught. And our vector v is some direction vector for the line, given by a, b, c. So if I take these three expressions and plug them into our equation, our vector equation for the line, then what we get is that r equals r naught plus tv boils down to x, y, z is equal to x naught plus ta, y naught plus tb, and z naught plus tc. And so just comparing their corresponding components, we get that x is equal to x naught plus ta, y is equal to y naught plus tb, and lastly z is equal to z naught plus tc. And those are the equations that are written here. These are known as the parametric equations for the line. Now we will often interchangeably use the terms vector equation and parametric equations for the line because really one is just an unpacking of the other one. They essentially contain all the same information. It's just whether we've looked at them as vectors as a whole versus the individual components. The last way we could describe a line, now you notice with these previous two there was this parameter. There's this parameter t that's helping us get various points on the line. For various values of t we get various points on the line. When we think back to 2 dimensions, our equations of our lines were things like y equals mx plus b. So they involved just the variables y and x, whereas we didn't use a parameter for them, at least not initially. We did when we got into parametrized curves. We looked at other ways to describe them, but at the start we looked at equations of lines as things like equations in y and x of the form y equals mx plus b. What about in this case? Could we describe lines in that way as well without the use of a parameter? And the idea is, yes we can, but it's not going to be given by a single equation. A single equation would describe, so in 3 dimensions, a single equation describes a 2-dimensional object, whereas a line is a 1-dimensional object. So if we wanted to have a way to describe a line without a parameter, these are known as the symmetric equations. And I'll just leave our parametric equations visible up above, because what we do to get our symmetric equations is we just take our parametric equations and we solve for t. Or another way to say this is we eliminate t. So in our first equation up above, x equals x naught plus at, if we solve for t, we get x minus x naught over a. And that's this first bit. That's equal to t. And similarly for the second equation involving the y minus y naught over b, that's equal to t as well. So each of these things is equal to t. So we could add a little equal to t on the end because that's really where the parameter went. So this is a way to describe a line without using a parameter. We will rarely ever use the symmetric equations. I'll do one example where we write them down, but we're hardly ever going to use them. We're mostly going to be focused on the parametric equations or the vector equation, which I first gave up above. Alright, so let's get to some examples. Let's write down the parametric equation of the line that passes through these 2 points. So we got a point 1 and a point 2. Now the idea is, to get a parametric equation, we need to know a point on the line, and we need to know the direction that the line is going in, so a direction vector. We already have a point on the line. In fact, we have 2 of them here, so we're free to choose either one. A direction vector, we'll just take the vector that goes from one of the points on the line to another point on the line. And we can get this by doing the tip minus tail, so the position vector for the point at the tip minus the position vector for the point at the tail. And so our vector is -3, -1, -2. So there's our vector in the direction of the line. That means our equation of our line. We can write it, I can use a vector equation. So our line is going to be one of the points on the line. I'll use P naught for that point. And then we add to that t times the direction vector for the line, which is t times -3, -1, -2. So this becomes 1 minus 3t, -t, and 2 minus 2t. If we want to write down the parametric equations, as I said, we use these terms interchangeably, but here, since we just followed our definition of parametric equations, that is, we're just pulling off the components. So x is equal to 1 minus 3t, y is equal to -t, and z is equal to 2 minus 2t. Now, we can plot lines in math3d.org using this vector equation. So let's go ahead and add an object. It's so tempting to click on line here, but we're actually going to want to use the parametric curve tool. So we click parametric curve. I'm going to get rid of the surface that's already drawn. And now we just enter in those components of that vector function that we've just worked out. And there is the line that we wanted to find. We can even go further and check that that's the line we wanted by plotting the points that we wanted it to pass through. So we wanted the line that passed through the point 1, 0, 2. So this is 1, 0, 2. And we also wanted it to pass through the point -2, -1, 0. So -2, -1, and 0. And there it is. So we got the equation of the line that passes through those 2 points, and in fact we got the equation written as a vector equation. Okay, so let's have a look at this next example. Determine whether the 2 lines given here are parallel, intersecting, or skew. What is skew? Skew just means they are not parallel and they're not intersecting. So the way we do this is we proceed in the order that's given there. We want to know, are they parallel? Well, in order to be parallel, they have to have the same direction vector. So what I'll do is I'll just read off the direction vector from each of these equations. The direction vector for the first line is, we just look at the coefficients of t. That's going to be 2, 2, 3. So that's the direction the first line is going in. Our second line, it's going in the direction 3, 2, and 4. And then we just notice that V1 and V2 are not parallel. They're not pointing in the same direction or even in opposite directions. They're not parallel. So the lines are not parallel. So the lines are not parallel, which means now we want to check, do they intersect? Well, what would it mean for them to intersect? Well, it would mean that there would have to be a common point on the 2 lines. So there'd have to be some value of the parameter t, which when I plug it into the first equation for the first line, it gives me a point, such that when I plug in a value for the second parameter t, it could be a different value, I get the same point. So what that means is if they intersect, then there exists values s and t such that plugging s into the first equation gives me the same point that I get when I plug t into the second equation. So I would get 2 times s, that's the x component on the first equation. That would equal 5 plus 3t. And I'd get -1 plus 2s has to equal 1 plus 2t. And I get 3 plus 3s is equal to 4t. So there has to be some value of the parameter when I plug it into the first equation. Gives me the same point as plugging another value of the parameter into the second equation. Who knows, s may be equal to t, but in general, I'm not assuming they're equal. Okay, so that means we've got a system of equations to solve. So system of equations. The first equation is 2s minus 3t is equal to 5. The second equation is 2s minus 2t is equal to 2. And the third equation is 3s minus 4t is equal to negative 3. Now, how do we solve a system of equations? The most straightforward way now, since you're involved in linear algebra, either this term or if you've already done it, is to go ahead and form an augmented matrix. And so that would be 2, negative 3, 2, negative 2, 3, negative 4, against 5, 2, and negative 3. The first column represents s, the second column represents the coefficients of t. And so there is our system written as an augmented matrix, and then we go ahead and use row reduction to try to get the solution to the system of equations. So what I'm going to do is I'm going to notice that I can take negative the first row and add it to the second one to zero out the entry in the first column. So negative the first row, so negative 2 plus 2 is 0. Negative 3 is 3, plus negative 2 is 1. Negative 5 plus 2 is negative 3. And I will also take negative 3 halves times the first row and add it to the third row to get a 0 there. Negative 3 halves times negative 3, that's 9 halves. 9 halves minus 4, or 9 halves minus 8 halves, is 1 half. Negative 3 halves times 15 is negative 15 halves. Negative 15 halves minus 3, so that's negative 15 halves minus 6 halves, or negative 21 halves. And it's from here that we see t is equal to negative 3. That's what the second equation tells us. But the third equation tells us that t has to be negative 21. These are not equal to each other. So that means there's no solution. Therefore, there's no solution. Since there's no solution, it means that there was no value of the parameter for the first curve and a value of the parameter for the second curve which produced the same point. They don't intersect. So therefore, since they are not parallel and there's no solution, in other words, the curves don't intersect, therefore the lines are skew. So we'll just write down here that what we did is we found that they don't intersect. That's what we did by solving that, or showing that the system of equations has no solutions. They don't intersect, and therefore the lines are skew. Let's get a visual for what it means for the lines to be skew. So we'll go ahead and we'll add a parametrized curve, and we'll just write out the curves that are given. And then the next line, so zoom out a little bit. So there's the lines. So we can see they're not parallel, they don't point in the same direction. They also don't look like they're intersecting. If they do intersect, it's going to be quite far away. But what we found is that they don't intersect. So if I kind of look at it from, the side, it looks like they're never coming together. And we verified that. We verified that they don't intersect. So this is what it means for the lines to be skew. They don't point in the same direction, but they're also not coming together and meeting at a single point. So these lines are skew. All right, let's have a look at the next example. Again, we want to check, are they parallel? Do they intersect, or are they skew? So we'll look at our vectors again. The direction vector is 2, 2, 3. And in this case, it is 3, 2, 4, so same as they were before, and therefore they are not parallel. One vector is not the scalar multiple of the other one, and so they are not parallel. Do they intersect? Well, that means there'd have to be a value of a parameter, which we plug into the first equation. So that would be, let's say, a value s for the parameter. That I get the same point when I plug in a value for the parameter in the second equation. Let's say t is the value that goes into the second equation. And so I need that equation to be true. I need 3 plus 2s to be 1 plus 2t. And I need 4 plus 3s is equal to negative 1 plus 4t. So the system of equations is going to be 2s minus 3t is equal to negative 4. 2s minus 2t is equal to negative 2. And 3s minus 4t is equal to negative 5. Go ahead and write that down as an augmented matrix again. So that's 2, negative 3, negative 4, 2, negative 2, negative 2, 3, negative 4, negative 5. And then the row operation we're going to do is we're going to add negative the first row to the second. And so that gives me a 0, a 1, and a 2. And then the next row operation I'll do is I'll multiply the first row by negative 3/2 and add it to the third row. That gives me a 0 here. Negative 3/2 times negative 3 is 9/2. 9/2 minus 4, that's 9/2 minus 8/2, which is 1/2. And then I get negative 3/2 times 4, which is 6. 6 minus 5 is 1. And we see that the second and the third equation are actually the same. They're really just the same equation. One is just scaled, a scaled version of the other one. So what I can do is I can get rid of that equation, the third equation. I will just multiply the second row by negative 1/2 and add it to the third row, and I get 0, 0, 0. What else I could also do is I could add 3 times the second row to the first row. So that would give me a 0 here, and 3 times 2 is 6, added to the negative 4 is 2. And so now I can read off my solutions. S is equal to 1, and this tells me that t is equal to 2. So they do intersect. They do intersect. They intersect at what point? Well, I can take S and plug it into line 1, or I could take T and plug it into line 2. However I want to work out that point. In fact, a good check would be to do both. So let's plug S into the first line. So that would be 4 plus 2 is 6, 3 plus 2 is 5, 4 plus 3 is 7. But I could also plug t equals 2 into the second equation, or the second line, and I get 3 times 2 is 6, 1 plus 4 is 5, and negative 1 plus 8 is 7. So I get the same point, and that's just a double check to make sure I didn't do anything incorrect, make any typos along the way. So we got that they do intersect. So these two lines, they intersect, and they intersect at this point. We could plot these things to also check this as well. So we'll get rid of our, well, actually we'll keep our lines from before because I'll just slightly update them. So the first line is 4 plus 2t, and then 3 plus 2t, and 4 plus 3t. And then our second line is 3t, 1 plus 2t, and negative 1 plus 4t. So there we go. There's our two lines, and yeah, it looks like they're intersecting. Let's get a better view of where they're intersecting here, maybe something like that. What's their point of intersection? Might be kind of hard to read off by just dragging this around, especially since we don't have our axes extending very far. But we did work it out, so we can go ahead and plot that point. That point we found was 6, 5, and 7. And we'll change the color, maybe make it a little bit bigger to see, make it size 36, and sure enough, we found that intersection point, and there it is. So that's a double check that our calculations actually contained no errors. Alright, let's have a look at the last example for the lines. So we're going to find the parametric and symmetric equations of the line that pass through these 2 points. So let's call these points something. Maybe I'll call this point P and this point Q. I want to find the equation of the line, so the first thing I want to do is find a vector in the direction of the line. Maybe I'll take the vector that goes from the point P to the point Q. So that would be tip minus tail, so -2, 1, -2, minus 1, 2, 3. So that vector is -3, -1, and -5. So for our line, I would like to use the vector equation, and then from that get the parametric equations by just unpacking the components. So what is our vector equation? We need to know a point on the line. We can choose either of the points we've got here, so maybe I'll just choose the point P, so 1, 2, 3, plus t times a vector in the direction of the line. And so there is our vector equation of the line. I'm just going to put them all into a single vector. So that's going to be 2 minus t and 3 minus 5t. And then in terms of parametric equations, the parametric equations are x is equal to 1 minus 3t, y is equal to 2 minus t, and z is equal to 3 minus 5t. The symmetric equations we get by just solving each of these equations for t and then setting them equal to each other. So this will be x minus 1 over -3. That's equal to y minus 2 over -1, which is equal to z minus 3 over -5. So there's our symmetric equations. We're interested in what point does this line intersect the xz plane. So where does it intersect the xz plane? Well, this happens when y is equal to 0. And so when is y equal to 0? Well, I can go back up to my parametrized form of the line and look at the equation given the y value. So this is when t is equal to 2. So the intersection point is given by r of 2, which is 1 minus 3 times 2, so maybe we'll write it out and then work out the values. 2 minus 2, we already know that's going to be 0, and then 3 minus 5 times 2, or 3 minus 10. So in other words, it intersects at 1 minus 6, or -5, 0, -7. So the intersection point is just given by changing the brackets from angle brackets to round brackets, so now it's a point. Alright, so that's it for the first half of this section. We've just focused on lines. In the next video, we will focus on planes, how to describe them in three-dimensional space, and the kinds of equations we can use to represent them. Alright, we'll see you in the next video.